So as an engineer, I'm actually more interested in the flow field in the inside as predicted by the model, because that tells us a lot from operational point of view whether there will be any problems or not. And the bottom one is the pressure field, so that's also a good indication. But the purpose for me showing this is not to discuss how these calculations are made. Those are available in the paper and the references in the paper, and these are to the CFD specialist. They will be able to interpret it do that much better than I can do, because I'm not a modeler myself. But I'm looking at the actual predicted values as an user and nothing else. And then there are the other ones are the as a function of the gas velocity going in, what is the filtration efficiency looks like. They call the term initial filtration efficiency. I could not figure out exactly why they continue to call it initial filtration efficiency as opposed to just filtration efficiency. But the important thing in here is that in your filter, if the filtering medium has this sort of particles, 1 micron, this is the particle sizes that go in, then which one will be separated at what efficiency, that can easily come in from this sort of prediction. So for example, the larger particles are separated at a higher efficiency, at a higher range of the velocity. So again, I look at these predictions to find out how we will be designing it, how we will be operating it. Because if I know what is the size of my particles in the gas, which I can measure from diffraction sizing, etc., then I can predict, okay, if this is, I get the highest filtration efficiency, highest separation efficiency, if I operate it at this velocity, then that's what the velocity I will be using for my design and of course for my operation. So that's how we look at it. But in the upper one, which shows the velocity field, the flow field, essentially, that will tell us, that's telling us that during the operation, if there are any excursions or not, there are any significant variations or not in both velocity as well as in pressure, because if that happens, then we'll have to minimize it, otherwise the candle elements can be in trouble. So that's how you will be looking at all of these predictions. And then I have copied another one. This is quite beautiful as far as the practical implication is concerned. So they have all these different particle clusters, the filter medium particle clusters, and then at different velocities of the gas, 1 meter per second or 0.2 meter per second, etc. And at different time, after 1 hour or after 2 hours, or for that matter after any other hours, how many of the particles in the incoming gas will deposit. That's what this sort of figures are showing. So that's another very important prediction, because that will affect what? That will affect my purging sequence. How much gas I will purge, at what frequency I will purge with nitrogen to clean up everything that has been deposited on this filters, first row, second row, third row, etc. Okay. So any question before I go to the next step on the on this cleanup? No. So the way I take it is, all the discussions that we are having is that models are there, and models will give you the numbers that you want based on the assumptions that you feed in. That those assumptions have to be very, very realistic, and those assumptions have to be, if they are not realistic assumptions, they are not practical assumptions, then your model predictions will be varying. So therefore, it is very important that the model predictions and the experimental data are usually generated from the same source, if possible. Then you know what is wrong in your experimental data. The problem that you are facing perhaps is that the experimental data is suspect. They may have just given the average or one extreme, the highest level, which they could show beautifully to the rest of the world that this is what we are getting. And your problem is that you are not matching with that. So from that point of view, it always does make sense to, if possible, to have the experimental group and a modeling group work close to one another. There are pitfalls of developing a model, validating it with someone else's data. Some cases they work, in many cases they don't. Okay. So far we have given you, we have told you what are the generic issues with respect to gas cleanup, what are the pollutants, why cleaning is necessary, what are the pollutants, solid as well as gas, in order to take them out, what type of filters you are currently used, what is the temperature range of each of the filter types. So those were until the last week, and then today is a little bit further as far as particles are concerned, that discussion. So that's done. Now let's stay on the same theme, but let's discuss the gaseous pollutant control, and more on that. So if you can recall, on the hot and warm, on the sulfur control, people have been using the zinc and copper and nickel and all sorts of other metallic filters, as I showed in one of the slides from last week, which is now part of this overall presentation. So here I'm giving you some examples from where the large research providers, what type of systems and what type of metals the large research providers have been using. So it's a collection of information generated, collated from sources which are prepared by the large bodies, large research institutions, okay, not from small research group. So RTI in US, they demonstrated this is also all about sulfur control. They demonstrated the zinc-based technology, zinc-based material filters for, but only at 500 to 1000 Fahrenheit. So 500 is about 260 Celsius. And 1000 you should be able to calculate, I think it's under 800. definitely. So 1000 minus 32 divided by 9 times 5. So you should be able to calculate it that way. But their filtration system is based on either a fluidized bed or in packed bed, and they have demonstrated that if it is the zinc-based particles for sulfur control. So now we have come away from the metal filter. We are now talking about the specialized filters. That this can work in either fluidized bed or packed bed. Both will provide the adequate mixing or contact between the incoming sulfur gases and the particles in the bed. The bed, as you would expect, will obviously be filled with something that can tolerate the sulfur gases. So, your question is why ESP is not used, or why I am not talking about ESP being used in here, right? So can anyone tell me why you think ESPs cannot be used? Pressure. PF-fired boilers, PF-fired furnaces work at atmospheric. Gasifiers, ESPs wouldn't like high pressure. But it's a good question though. See, if you don't ask the question, then we don't know even that this can be an issue. It's a very important question. Sorry? So another question then. So let's discuss it. Can gasifiers be operated at atmospheric pressure? So gasifiers have been operated at atmospheric pressure. So why people operate gasifier at higher pressure? Compact. So compactness, because it will become smaller. So is that the only advantage, Madhu, you think? The gasifier designing it at higher pressure will definitely make it compact, but will that be the only advantage? Yeah. True. What else? Okay. So I am the client giving you the money as an engineer or designer, and I tell you that, look, this is what I want gas, carbon monoxide and hydrogen and blah, 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 etc. You tell me what type of gasifier and what sort of pressure. How will you decide that this should be 1 bar or 5 bar or 25 bar or 30 bar, etc.? What will decide that? Yes, that's right. So it all depends on how I am going to use the gas. Because if I need the gas at high pressure, obviously I will have to run the gasifier at high pressure. Otherwise, the only other alternative will be run it at atmospheric pressure, cool the gas down all the way to ambient, and then compress it. And then you as a design engineer carry out the techno-economics, and then you then decide which one is more economical. So if it is atmospheric, then all the answers that you have given is correct, that will be large. And then if it is pressure, it will be compact, so that's also correct. So you have been telling a lot of correct information, telling a lot of correct, making correct statements. A little bit is you should ask the client, what do you want? Okay, well, do you really need, what's your application? Does it need pressurized gas? Then I can decide whether to do it a very large gasifier or a smaller, higher pressure gasifier, and then I can do the calculation, techno-economics calculation, and then tell you which will be cheaper capex wise, which will be cheaper opex wise. But it's that will be your starting point. So let's then move on to the second point here. The Power Systems Development Facility is called PSDF at Wilsonville in Alabama. They actually tested the transport reactor, the larger one, larger than the one that I was involved in operation at North Dakota, but exactly a similar configuration. And then the scaled up version was built over there. And there they used for sulfur removal catalyst supplied by one of the commercial companies, Sudchemy in this instance. But they found that the Sudchemy catalysts give the exit concentrations below 10 ppm, but there are other PuroSpec 2010 or PuroSpec 2020 resulted in less than 1 ppm hydrogen sulfide. These are all zinc-based beds, zinc-based compounds that they have been using. How they prepare it, that's all commercial secret. Neither Sudchemy nor Syntex will actually tell you. Syntex is, the Syntex is now part of Johnson & Matthey. Johnson & Matthey, as you know, is one of the largest catalyst supplier. So the bottom line message from here is that you can get very low hydrogen sulfide ppm by using warm sulfur gas control, but the temperatures are still low. We are looking at sub 300 degrees to do this. Then the Gas Technology Institute, GTI, demonstrated zinc titanium sorbents to get less than 10 ppm. ConocoPhillips tested proprietary sorbents on a slipstream from the e-gas system at Wabash, and I took these statements from their reports available at the NETL website, but they don't actually say exactly what the material of the sorbent is. My suspicion is that, not suspicion, my feeling is that they're all zinc-based ones. Then of late, in the last 5-6 years, this is for the development of the Japanese gasification industry, and there are quite a few. Not only Mitsubishi, but Hitachi is another competitor within Japan to Mitsubishi. Then before that there was another one, and I'm trying to remember the name of it. I forgot anyway. If I could remember, then I will tell you later on. But they have the Waseda University for the R&D done for the Japanese gasification companies was demonstrated for a syngas with a zinc ferrite sorbent to less than 50 parts per billion. Small scale work, but that's a massive cleanup. It's a massively efficient cleaning system. So whether that is, I haven't seen any proof that it has been tested at larger scale in MHI's Nagasaki lab, Nagasaki R&D facility, where this MHI's 3-meter one and the much larger one is located, or Hitachi's Wakamatsu facility, which is in an island just below Japanese mainland. Whether they have tested this at the large scale, no indication. Maybe they are testing. Usually these companies and their R&D providers, they come up with public release when they got substantial amount of information generated and are validated. That way the Japanese, what comes out from Japan is very, very credible. They do not provide sanitized data from my experience. Okay, so any question before I move to the next slide? So it's very important then that for sulfur control, there are technologies which are available that can take you to very low ppms. I mean the sub 1 ppm level already. And that can be done using any of the types of the reactors, because it's one thing to develop the metals, the sorbent material, but it's another thing to actually design it. For that you need to know what type of reactor you will be using, whether a packed bed or a fluidized bed or a transport bed. So what is a transport bed versus a packed bed? Who can tell me? Here I'm talking about the not about the transport gasifier or a fluidized bed gasifier or a packed bed gasifier. I'm talking about the reactor that you will be. So why would you need transport bed for sulfur cleaning? Because obviously you would not need like what happens in a transport gasifier, where the material goes to the top of the gasifier and then comes back. Yeah, I think we are getting the answers now. So gas solid contact is another one. So the transport beds definitely will give you much better gas solid contacts, almost as good as what you can have from the fluidized bed. But the transport beds will be a little bit more complicated in its design, in the sense that some of the catalyst particles for sulfur control may get completely elutriated from the bed, and you need to bring them back into the bed quickly. Okay, and that's what I think all three of you have been saying. And so Okay, so how do you quantify then the contact between the sulfur gas and the catalyst bed will be better compared to the contact of the same two in a packed bed? That's your question. So, no. So the difference between the packed tower and this one is completely different. So it's a very good question. Yeah, yeah, yeah. So packed tower is a completely different operational regime, completely different design regime. Here we are in the packed tower. There is no individual particles. Here we are talking about individual particles of the catalyst, which could be zinc based, which could be arsenic. So, but before I start talking, can anyone have any ideas? Yeah, is that right? Yeah, I think everything that's being said is correct. Something else? Yeah. Yeah. So, but I still haven't got the answer. Everything that you have said is correct, but I don't think I have got an answer which will make Dr. Dave satisfied. How do you make sure that the contact is better in this versus that? Have you got that answer, Dr. Dave? Is it? No, I haven't. Yeah. Yeah. So apart from concentration of what? Yeah, that's fine. So concentration difference of sulfur species between the bottom of the bed and the top of the bed will tell you what is the sulfur capture. So that's fine. That indication will always be there. Yeah. Yeah. It's quite fascinating, actually. I really appreciate that you are volunteering to give your views, and that's how we all collectively progress. So that's fantastic. That's absolutely fantastic. But also, I'm noting a trend that you have the ability to go into the depth of the matter very quickly, which is also good. But sometimes you have to. Yeah. Yeah. Okay. So to answer your question, in any of these beds, the first thing that is seen are the instrumentation that is kept, the pressure drop instrumentation, and it is the pressure difference that tells you whether there is good contact or not. So if the pressure at the bottom of the bed and the top of the bed are exactly the same, not much contact is happening. The gas is coming and push it going out. And then it has been said that you have to have finer particles which will give you higher specific surface area, because it will be a chemical reaction and kinetically controlled chemical reaction. Absolutely right. And in order to do that, that will obviously come at a cost, because the finer particles will give you pressure drop, more pressure drop. But that's fine, as long as it is within acceptable limit, then that pressure drop actually helps you in making the flow from one direction to another. Without flow to happen from one direction to the another, right? So that is also correct, but it is also correct that if it is too fine a particle which is necessary for good capture, which can give too much of a pressure drop, which can be counterproductive, then the way to prevent the particles from agglomerating with one another is actually to keep them fluidized in either the fast fluidized regime or in the transport regime. And if you have in the transport regime, because you are using too fine a particle, you need to bring them back through a small recirculation leg of its own. So it all boils down to what size of filter particles you are using. If you are using a filter particle which is quite large and still capable of doing the reaction between hydrogen sulfide and that particle material within a reasonable time, go for packed bed. Easy to load, easy to clean, easy to operate. But that often doesn't happen. Then you have to consider, okay, this is the supplier of my sorbent for the next 10 years. You need to have that contract. Otherwise, if the manufacturer all of a sudden goes bust, then you are in trouble. So you need to have a consistent supply. So depending on that, you decide whether you will be operating it, designing and operating it as a fluidized bed or as a transport bed. So remember, I have deliberately written in here as the bed rather than reactor. Of course, it's a packed bed reactor, fluidized bed reactor. It's a transport bed reactor, but I have avoided the word reactor at the end to sufficiently distinguish it with the gasification discussion, that this is a much smaller bed to facilitate a good interaction between the sulfur gas and your solvent. So how can your question is, how can we say that more pressure drop is good for mixing? So who can comment on this? So the key words here is actually the better mixing. And if, okay, pressure drop is a relative term. You can have acceptably high pressure drop and still have good contact. And if you have a completely slumped bed, because the particles have just agglomerated, then there will be nothing will flow through it. But at least if everything is kept fluidized, it will ensure that the gases will flow uniformly through all the particles, and that there won't be channeling of the gases through the sides or through the ends. So, pressure drop and a consistent pressure drop is a very healthy indicator of, is a very important indicator of the health of your fluidized bed reactor, whether it is a fluidized bed catalytic sulfur capturing reactor or some anything else. For exactly in the same argument for the pack tower. Even though the application is different, but the principle is still the same. Correct. 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 The So what is distribution quality? So that's for the pack tower. Yeah. 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 Correct. So here what happens is there is a difference between that pack tower and the packed bed reactor and all. Let me go one step back. For better gas solid contact in a kinetically driven process such as this, you'll be much better off to use fine particles of the solvents. There is no denying that. But the fine particles of the sorbent means you cannot operate them at a low velocity because the gases will not go beyond the first layer or second layer or third layer, and then the other layers will simply remain stationary. So you have to go on increasing the velocity. You may see that for that particular size, and Professor Shah, remember, showed the Geldert CBAD, all, depending on where this particle size is, you may then find that a certain velocity that takes me only into the fluidized bed zone is good enough to have good gas solid contact, which is the major aim for good operation, efficient operation of this unit. Right. You may find that normal fluidized bed range velocity is not good enough for this fine particle. We need to operate it at an even higher velocity, taking it into the transport bed. Either way, which velocity you will be operating, that will be decided at the design stage, but during operation you will have to keep a very good eye on the pressure drop measurements across the bed, and that's not just two tapping point, two pressure transducers, the range of them at the same level at different diametrical locations. So that will tell you the health of the uniformity of the pressure drop. That will tell you the health of the bed. Whether it is a fluidized bed or transport bed, that will be dependent on the particle size that you have chosen, the sorbent that the manufacturer is giving you. The manufacturer is telling you that this is the sorbent that we have tested, we are giving you guarantee. This is the sorbent about 5 to 10 micron range, will give you a very good sulfur capture. For that, you decide whatever regime you will be operating, whether packed or fluidized, possibly not packed. maybe fast fluidized or maybe transport. But that's on the design side. During the operation, you will have to ensure that once it is designed, that you are actually maintaining, you are observing that the pressure drop is uniformly maintained all the time. If there are significant variations from time to time, then it will be a matter of regenerating that the materials from that bed. And in many cases, what happens is you actually keep 2 into 100% beds running in parallel, I mean available in parallel, one operating, one standby. So standby one comes into operation, whereas the operating one goes into the regeneration mode. So this is all quite subjective, but I wanted to foster this discussion in here, that as to how you will select this by simply having 2 words in every one of this, because it's very, very difficult to capture it otherwise. Usually the sorbents are very low size, 20, 30 micron at most, because these are all fabricated. These are all made in the R&D facilities of whichever company, BASF or Sud-Chemie or Johnson Matthey or others. So they will give you day in, day out quantities. They will take those back again if necessary, and then they will bring them back to you through a proper contract. But the important thing is they will also tell you that, look, this is the size that we are giving and you need to operate it in this one or that mode. And accordingly, they will give you the design, which will be verified by the design engineers. Usually it comes at a package. It's not. If the particle size is large, you can go for the packed. But if you will not go for transport. Yeah, I mean the packed one, in order to keep them in transport mode, you will need a lot of gas velocity. Yeah. If you have the velocity available, then you will use the transport bed. Okay. And if not, then you will do it at the fluidized bed. But they can actually tell you that, look, this will be much better suited for this regime or that regime, because they have done this through their testing modes, that in this fluidization or contact regime, the best contact is made, and therefore it will give you the best possible sulfur capture. Anything you deviate too much significantly, then it will not give you the performance guarantee. So gas volume is fixed by you as the client, and they will tell you that, look, this is the size of the particles. Then you can decide whether you make a tall and skinny one, tall and small diameter, tall one but very small diameter one, that will have its own maintenance issues, or have a reasonable size and not so tall ones. So those are the considerations, and you can then decide what you will do. Because if you have a tall one, then it has got some other implications for its support, the tall support and wind loading and everything. that you will have to follow design following the codes. So that's how it is. So there is no one size fits all. So that's why I haven't written anything. You have to appreciate what are the issues are, and in conjunction with the supplier, in conjunction with the designer, you then decide, okay, this is what we will take. So you are not, once the plant is designed, you are not increasing the fluidization velocity. Fluidization is always fixed, yes. How else can it increase? Unless you are generating more gas, it cannot. Or unless you are putting in more nitrogen. You will put in only more nitrogen to parch at times. But otherwise, it's all fixed. So if pressure drop changes over a period of time, that's telling you some problems have been happening. You'll have to look after the bed. Some problems are happening. At usually, if you at several levels, 2 or 3 different levels. No, you will have more than one measurement at the same level, because you see, if something happens to only one at one level, then you will lose control on everything. To start with, at the start of the operation and for certain periods, it will be all, when everything is fine, it will be all be giving you consistent set of pressure drops. But over a period of time, the pressure drops will start changing, and there will be correct. Expected to be, what is your diameter is not this much, but this much. You cannot expect that the flow in here, flow in there, will be exactly the same, because your catalyst particles are also undergoing attrition over a period of time. So there is a fluidized, continuous flow. Then also, so you can't expect that today, if you talk July, it is fluidizing, we have started fluidizing beautifully, 15th of July or 15th of December, it will be fluidizing exactly the same as systems will change. So that's why the instrumentation is there. There is one thing, other thing is that this transport design and all, it may require a specialized construction of the whole system, right? For the transportation of the wet material facility to the number. So it cannot be possible that simply we can just shift the factor into. No. There is a whole everything is completely. So that's a design issue. So that when a bed, a particular one, goes into standby mode, the reason it goes into standby mode so that it can be cleaned and that it can be cleaned easily, relatively easily, and then replenished. So those are physical, mechanical design things. So you have to provide the manholes, for example, and so that the manholes can be covered, and then if required, a person can go inside it. So if it is a tall and skinny one, it will be difficult to do it that way. So a whole lot of considerations that eventually go in. The client may say that, look, let's explain the easiness of the cleaning of this bed, how easy it is. So that's purely mechanical design. But here what we are discussing is that solvent particles have come from the manufacturer at a certain particle size, and in order to keep it fluidized very well, what should be the size? And then we will decide, okay, is that size, is that volume makes it amenable to cleaning and maintenance easily or not. That's another level of design issue. If not, then go back to the drawing board and then say that, look, this is too small, let's have a broader one, and broader one means possibly it's going to be not a taller one, it's going to be a shorter one, then the residence time can be different, and then how can we provide the same required residence time into a larger diameter, shorter one. That's a mechanical internal designs, putting in baffles. So those are different issues which we are not even touching here all that much. But that's how it is done. Any other question from anyone? Okay, so let's go to the a little bit of a cost figure that I have been able to give. People usually don't give much cost figures. CapEx, I could not find anything. The operating cost of warm gas desulfurization, this is the NATL figure that they've been quoting, which is nothing. But so this is the operating cost. I could not find anything for the CapEx. I suspect the CapEx will be quite large. But what they say is that because of the removal of these gases, which otherwise creates problems and requires deeper condensation of the gases, you won't need any deeper condensation. You be at warm gas, you'd still be able to do it at a certain temperature, even though it is warm gas. So your thermal efficiency will be 1.7 to 2.7%, depending on the gasifier type. So don't look at those figures any more than, because they can, specific cases they can vary, any more than the fact that if you didn't have warm gas desulfurization, the only other way was to cool the gas all the way down to ambient, and that way you know that it will be shear short more or less. If that be the case, you will be losing a lot of efficiency, not just the exergy efficiency, and compared to that, doing it at a higher temperature will give you some efficiency improvement. That's how I will look at it. The OPEX is anybody's guess. It's hard to believe 0.1 cents per kilowatt hour. Hard to believe. But then again, who am I to dispute it? So, and then more on the halide removal. So we discussed about the chloride removal in particular last week in the slides. So this is the upfront comment I am making. Halides are what? Salts of Chlorine. Okay. Salts. That's correct. Anything else other than salts? Huh? Alkali halide is also a salt. Yes, that's right. That's right. So hydrogen chloride is another source of hell. See, you guys know it all. I mean, I don't have to. But if I don't push you guys, then you won't be able to tell you. You guys are hoarders of information that don't like to tell unless you are poked to tell. Okay, so. So the sodium based, so the first point I make is that you can clean all of this up below 1 ppm by conventional water scrubbing. So just bring the gas, put it into a spray tower, spray water from top, and then it will take out the halides. In all probabilities, it will also take out the sulfides. It will also take out something else. But if you don't have access to a lot of water, or if you don't want to do that, then this is the other alternatives. Trona and narcolite. What are those ones? I did not write them. What is this? I did mention about narcolite the other day. This is sodium based. Anyone from this side? Yeah, sure. But trona and narcolite are something that you can detect in diffractograms. These are not commercial names as such. So these are actually different types of carbonates of sodium. So they can reduce the chlorides to less than 1 ppm, but only from hydrogen chloride, as you would expect. I mean, they won't take it from sodium chloride. So if hydrogen chloride is the predominant source of chloride, and which it can be, because not all coals have significant amount of sodium, but all coals have reasonable amount of chlorine, and that chlorine comes out during the just after the pyrolysis phase, around 600 degrees or so, about hydrogen chloride. So those hydrogen chloride can be soaked, and it is sorbent. That means absorbing onto its surface by sodium carbonate of one description or the other, trona or narcolite. These are different types of same sodium carbonate compound with different degrees of crystalline water in them, or different amounts of water in their matrix, nothing else. But there was in the DOE's website and ETL's website, there has been mention of injection of soot chemi, one soot chemi chemical into a second particulate filter at 550 Fahrenheit. So 550 Fahrenheit is about 275 Celsius or so. Reduce the concentration of the chlorides to below 20 parts per billion, and the gas turbine manufacturers will love it to see that sort of things. And the Energy and Environmental Research Center at North Dakota, the EERC, have used commercially available chlorine guard bed to water shift catalysts. So whether is your downstream application is fuel cell or gas turbine or water shift reaction for chemicals synthesis, you need to have the chlorine guard bed, remove the chlorine, and these are some of the options. Either spray it over or use the sorbent bed, which will give you, again, you'll have to consider what type of bed that will be. depending on the size of the trona or narcolide. Usually they are very fine. So in all probabilities, you will be going to the fast fluidized bed or the transport bed variety, definitely not packed bed, unless you have made pellets out of those and then use the large pellets, 8-10 millimeter sized pellets into the bed. That will allow you to make use packed bed. So those are some of the other considerations. So the last point that I had with a lot of dots, afterthoughts, what works and what doesn't. That's what I would like you to think after reading all of these things, is which one you think may or may not work in your case. Will water spraying or using a water scrubber will work in my case? Will that be affordable? If that be the case, then obviously don't have to look at anything else. Then the question then is also whether it is water scrubbing or the sorbent bed. The bed material or the wastewater from the scrubber is getting extremely full of chlorine, right? Yes or no? So what do you do with that wastewater? What do you do with that chlorine-rich sorbent bed? Because you can't just throw it down the drain. Huh? Yeah, well, I mean, you have to think as to what you will do. So, if where will that chlorine actually go? I mean, for example, the second one, I'll come to the scrubber later. Second one is capturing the chlorine from hydrogen chloride, because you have found out that hydrogen chloride is the predominant chloride species coming from your gasification system, because that's how that particular coal is, or that's how this particular biomass is. So in that case, and that it is not sodium chloride, it is predominantly hydrogen chloride. So you decided, no, look, I will use this sodium based narcolide sorbent bed. So that is then producing sodium chloride, right? Sodium chloride is actually not toxic, that's for sure. So disposal will be a lot easier. So these are some of the afterthoughts of after selecting this. You have to keep in mind that how will you be regenerating that narcolide bed, which has now got very rich in sodium chloride. Washing may be a solution, which you can chlorinated water, I mean the sodium chloride water can be disposed. I don't think there is significant EPA restrictions at all. Same thing also applies for the water scrubbing. If water scrubbing is affordable, then the chlorine will be coming out as hopefully as sodium chloride, but if the chlorine comes out as hydrogen chloride, that's a problem. You cannot throw it down the drain, right? So these are the afterthoughts. This is what is meant by the afterthoughts. So again, the important thing is you need to know your fuel gas very, very well, in what form chlorine is present. Usually if it is hydrogen chloride, you are not looking at scrubbing, you are looking at capturing it at sodium chloride, right? Lots to come out together with hydrogen. Just like you two trying to sit next to each other, chlorine and hydrogen love each other. and they come out together. And, so there are very few calls to it all depends on how it is.
Usually they form a stable compound, just like carbon monoxide.
As stable as that, that's definitely stable. And
But then gives free energy is even low concept.
right. So simply because the chlorine is also very, very closely bonded to the carboxyl groups, which means it has carbon and oxygen and hydrogen. So a lot of the carbon can go out as carbon dioxide, can go out as carbon tetrachloride. Chlorine and hydrogen are the affinity. So let's quickly go into the next bits. We talked about last week about the ammonia and hydrogen cyanide. Again, the first point I make is that you can mention a lot of starting points when you have to regular temperature period. Whether you will allow that to happen, you as a doctor that is part of your afterthoughts. Here I am just giving the different options that are available. Whichever you choose will depend on your specific circumstances. The other one is the catalytic decomposition. Then the next one, in that, we have noted that nickel-based compound is a nickel-based catalyst by a particular manufacturer, probably having a brand name, commercial name of HTS1 at 800 degrees, you can dissociate ammonia by 90%. Then there is another company which looked at nickel ruthenium based catalyst, 700 to 900 degrees centigrade, and at a gas resonance time of 1 to 2 seconds. And that's a very important information. You usually don't find it. You can get 99% ammonia conversion. Because people usually give the already first figure, 99% or 90% or 95%. They don't tell you how many seconds it. As soon as you get that, then you are off to your design. Your design is, you have got everything. But in most cases, they only find it so they went to so the catalyst activity declined on this particular team, declined after 8 hours of operation. That was they were in the makeup, the element. And they needed to be regenerated through oxygen. And that brings it squarely into the area of the almost all the regeneration reactions are exothermic, so that's one advantage. Some catalytic decomposition by chlorine and calcium oxide removal, that's small scans, or just clean that.
Chlorine or iron?
Oh, sorry, it's iron actually. It's iron, not chlorine. Iron oxide, calcium oxide removal. You can do that at any temperatures about 500 degrees centigrade. But they haven't reported a bit, fair bit of the laboratory based investigations. But they do work quite well. So I would have to check that current level before so iron oxide actually has a very good catalytic two things. It is properly designed that even after breaking down the tar to smaller items, short it still remains effective, that you should be able to use it also. So, important thing in all of this is first and foremost, find out through equilibrium calculations what is the highest level these gases will exist when you are bringing them, subjecting them to processing at a particular temperature. That is the highest level that you can work at. Below that, to bring it below that will be very, very difficult. You have to have catalytic loss. That's what the catalyst will do. But the thermodynamic says the limit. So often it is most important, as we have in there, that if you have all of these gas mixes together, coming from the top of the gasifier, whatever temperature, then what's, of course you know how much is present there from measurements. Then if first thing you do is, if you pull it down, just without considering it, if you pull it down to temperature X, temperature Y, temperature Z, etc., then at what levels they will present. Okay. And then you start thinking, okay, what shall I do? Shall I use this current? Or shall I use this nickel platinum-based catalyst? Or shall I go for the cheaper, or the cheapest alternative of iron oxide, or calcium oxide-based catalyst? So eventually your decision will be based on taking economics here. Everything is possible. It is not correct to say that nickel and the lithium-based catalyst at 800 degrees centigrade is the one that I am recommending, unless it is complemented with proper arguments. The arguments are, yes, technically it will work, but is it also cost effective? So that's technical things that we will have to do. Let's take another couple of slides and then we will continue from lunch. I kept one slide back in here and bringing it back to this particular process flow diagram for the anti-electric biodiversity plant, Chloride. So it is a starry-fed gasifier going from the top. Everything else that you have seen, let's not worry about the heat steam generator, gas turbines, steam turbine, steam generators. Let's focus on this part in here. On the gasifier, you are pulling the gas down. So it's the syngas cooler wave. Then you have a raw syngas. Then what they have over there in that particular time, that is what cyclones and etc. are all here, which is not necessarily shown. And then, that for their particular case, they also get the sulfur species, a fair bit of it in gas, carbon, and sulfur, C4S. They cannot release it. So that's why they have to separate hydrolysis, COS hydrolysis unit, which is COS casting, giving the hydrogen sulfide and CO2. And goes through a series of units in here for final polishing, so that the clean syngas, part of it goes to this column in here. Let's not go into handling. The clean syngas goes to the final filter before it goes to the combustion. Final filter means taking all the factors out. So the portion which gets to the gas turbine for power generation, gas goes into two different directions, one to the gas turbine and one goes this way, other use for chemicals production. We'll come to that. The syngas that goes to the combustor has a final level of filling. So I'm not taking any of these parts together. No, H2S is removed. No, it's H2S is taken completely from there. That's not what I talked about. Here they have a filter, one particular filter which has taken out the sulfur. And here there is a scrubber system which does take out some of the sulfur gases, some of the chloride gases. But the final filter before going to the combustion, that takes out any residual particles that goes to the gas turbine. So the gas turbine is protected all the time, so let's not worry about it. Other part, they designed it flexibly, because what happens is they have the option to completely switch it off. Not generate the power. Sell the gas across the unit, across the boundary to next door neighbors and the and one of them is sulfuric acid. So there, they have different columns for the hydrogen sulfide having as it is. In that case, they use it only for chloride removal, not for sulfur dioxide, sulfur removal alone. Hydrogen sulfide is concentrated here from itself as well as what comes out from the sealants. And that then goes through this series of coolants. So just cool, and then it goes to a packed column, and then it comes out predominantly at everything condensed. You also have steam generation facility, steam unit here to regenerate. The net product that comes out in here is hydrogen sulfide and carbon dioxide, which goes to the sulfuric acid plant next. So they have they're designed to be flexible so that they can, if they want, they can generate all the power. This filter can be operated to take out the particles, but also inside the filter there are little plate which can take out the sulfur dioxide, the hydrogen sulfide. So they don't operate this unit and that unit. Yes. This gas is actually you can have CO and hydrogen, but it is here you are concentrating this hydrogen sulfide and this CO2 purely from the sulfuric acid production.
So that is the absorption power, and the solvent is generally the adjacent power.
Correct. So this is where the
So if they want to produce the gas, then you using that removal.
Right.
So in case of condensation or chemical reduction, the gas level is more rigorous as compared to steam the turbine. So what are the components that separate and distinguishes this two types of fuel?
So in both of these streams, one is very important, which is fly ash, will take a look, and the carbon and the chloride. That's why they have this way. Final filter will remove any very low particles as well as
whatever we go with this gas plus express plus you. So at the exit, why only express
I think they have just shown it so that that's what is attractive to the solid acid manufacturing. But then when I talk about in a couple of slides about the membrane separation, fundamentals of it, that how we can from a mix of gases consisting of these pollutants, hydrogen and CO2, different types of membranes which are available, who are the suppliers of these membranes, so we can take out through a series of membranes one after the other. We have another group which has very large group.
For all sorts of application. Gas, well, they use the polymeric ones as far as I know, but I'm not privy to the oh, yes. Gases, yes. Yeah. Gas. Yes, gases. Correct. Okay. So let's start after lunch. So after lunch, I would love to finish this section off, and then those who will be present. So if we have two, then I should be able to finish the other bit as well, the kinetics part, which I have been delaying. Okay. So let's reconvene after lunch.